PROMIS project, an international network for new efficient solar cells. The European Union, through Marie Curie scholarships, is funding research in renewable energies and their adaptation to the industrial market. In an era where most science fiction stories have become reality, the increasing energy demand is a major challenge for our society. Still today, fossil fuels are the primary sources of energy for our daily and industrial uses. Leaving aside their rarity, it has been established that they cause deep environmental damages. Solar energy offers a promising alternative. Each hour, our planet receives more energy from the sun than humans consume in 1 year. Over the past few decades, efforts have been pursued in order to harvest and redistribute the sun's energy. Nowadays, solar cells of square centimetre area can achieve record efficiency close to 50%. How does a solar cell work? The operation of a photovoltaic cell is based upon the internal photoelectric effect. In a semiconductor, such as silicon or gallium arsenide, the most energetic electrons are located in the valence band. That is, they are located in correspondence of the atomic nuclei, without the possibility to move away. If, however, they receive a sufficient amount of energy, they can jump into the conduction band and can move freely inside the solid. In a solar cell, the energy source that enables the electrons to jump into the conduction band are the solar rays. By choosing accurately the materials constituting the various layers of a cell, it is possible to generate an electric field inside it. When solar radiation strikes the cell, it is absorbed, allowing valence electrons to move freely inside the cell. Being charged, however, these electrons will be driven by the electric field generated in the direction of one metallic terminal of the device, from which they will be collected and sent to the opposite terminal, passing through an external circuit, thus producing current. This process can ideally be indefinitely repeated from the same cell. That's why we say that the photovoltaic is a renewable system. Now, let's take a look about how a solar cell is made. The fabrication of a solar cell requires a multi-step process. This implies a very strong collaboration between the researchers who take care of the different steps.
Different material properties have to be studied before designing a device, such as thermal conductivity, lattice parameter, and energy gap, that determines how much light is absorbed. In multi-junction solar cell, modeling is fundamental for finding the appropriate material composition of each layer for matching the energy of the solar spectrum. And in intermediate band solar cell, software can help us understand the effect of incorporating nanostructures in the solar cell.
Once modeled a structure, it is possible to grow it using high purity techniques, as molecular beam epitaxy or metal organic vapor phase epitaxy.
The high precision of these systems ensures a very high control on the thicknesses and the doping levels of the various layers that constitute the cells, thus allowing to perfectly reproduce the theoretical structure. Because of the need to have a high precision and purity, the growth of its structure takes several hours. It is also indispensable to make some preliminary characterizations on the ground structure, such as X-ray diffraction, before moving on to the next step. Where possible, we try to use cheap and readily available substrates such as silicon.
A light force roof of the highest precision is required for the solar cell processing. It is realized in a clean room through techniques that include chemical etching, chemical and physical vapor deposition, photolithography, ion beam deposition, and similar processes. The device evolution is studied at each step of the procedure. One cell can take up to several weeks of manufacturing. It is fundamental that the elaborated methods be compatible with the ones used in the industry, so that our solar cells will one day make it to the market.
Finally, the grown solar cell samples are modified to be electron transparent for characterization based on transmission electron microscopy. The analysis correlates the morphological and compositional properties of the samples to their functional characteristics and growth conditions. The final outcome provides us with insights on potential refinements for the whole process. Finally, efficiency measurements help us to compare the results and select the best technology.
Multiple iterations of engineering cycle are necessary to improve performances and to make a better device. If you want to find more information about PROMIS, you can visit our website or follow our Twitter.